Hello everyone, welcome back to the channel. Hope you are enjoying these lecture series. Yesterday we started with this topic called as ratio of specific heats, and we found out the ratio of specific heat for a monoatomic gas. We were doing for monoatomic gas, and for monoatomic gas we found out that the gamma value comes out to be as 5/3. Today we are supposed to do it for diatomic gas. The ratio of specific heat, that is Cp upon Cv. Cp is the molar specific heat at a constant volume, and Cv is the molar specific heat at a constant Cp is the molar specific heat at a constant pressure, and Cv is the molar specific heat at a constant volume. So let's get started. In case you haven't subscribed my channel yet, just subscribe the channel and keep following the lecture series. And if you are not able to follow any one of the videos, then it would be a request to go back to the previous videos, because all videos are linked together. Okay, so let's get started. So we are right now doing for diatomic gases. Now what are diatomic gases? Diatomic gases are gases which has molecules with two atoms. So there is one atom and there is another atom. So if there are two atoms and these two atoms makes a molecule, then that is called as a diatomic gas. Now in diatomic gases you will have to do two aspects. One, A, that is a rigid rotator. A rigid rotator, that means it can rotate, but it is a rigid rotator. And second, there is something called as non-rigid rotator. Now what is these two things called as? Now a rigid rotator is one in which the molecules do not vibrate. So if this is one molecule and this is another molecule, so these molecules, I'll draw it with a pen. Okay, so suppose if this is one molecule and this is another this is one atom and this is another atom, then these two atoms are connected by a bond, and these atoms do not vibrate. So yeah, these are called as the rigid rotators. But suppose if this is one atom and this is another atom, and these two atoms are connected by a bond, but that bond acts like a spring. This bond acts like a spring, so it can vibrate on both the sides. Then these are called as the non-rigid rotators. So there are gases which are behaving like rigid rotators, and there are gases behaving like non-rigid rotators. Like hydrogen and carbon monoxide are two gases which are which behave like a rigid rotator. Now let's go ahead. So in this video we are only doing for the rigid rotators itself. So we are on the A part. If you see, this is the A part. We are doing for the rigid rotators. So because it's a diatomic gas, I have taken that there are two atoms. So if you can see, this is one atom, this is another atom, and there is a fixed line. There is no spring effect between two atoms, and this entire thing is one molecule. Now if you just observe that this becomes my z-axis, x-axis, y-axis and z-axis. This is my x, y and z-axis. So this molecule can definitely move in the x direction, and it can move in the y direction, and it can move in the z direction as well. So it can move in x, y and z. That means it has 3 translational degrees of freedom. And the reason is because it can move in 3 possible directions. However, this molecule can rotate in this particular pattern, like around this axis. So around z axis it can rotate like this, okay, and it can also rotate in the y direction as well. So this is your y direction, this is your z direction, and this is your x direction. But yes, it can rotate in x direction as well, but x direction ka we are not going to consider, and I'll tell you why. See, rotational kinetic energy ka formula, that is E rotational, is half of I omega square. Now if you check, this formula comes from rotational motion, and this I ka value comes out to be 0 if the mass is distributed around the axis. So if this is the axis and the mass is distributed around the axis, then we can say that the moment of inertia is 0, because moment of inertia is mr square. So if mass is distributed very near to the axis, then r goes to 0. If r goes to 0, moment of inertia goes to 0, and if moment of inertia goes to 0, the rotational kinetic energy will go to 0. And if rotational kinetic energy is 0, then we are not going to consider that degree of freedom. So it will have one rotation like this, the other rotation like this, and it is not going to rotate around the x-axis. So we are going to consider only two rotations. So there are two rotational degrees of freedom. So there are two rotational degrees of freedom and three translational degrees of freedom. Now if you have followed my previous lectures, previous videos, you have understood that each degree of freedom brings in half kBt amount of energy. This is what law of equipartition of energy states, that each degree of freedom will bring half kBt amount of energy. So because there is 3, there is 2, there is total 5. So kinetic energy per unit molecule, that is kinetic energy per unit molecule is equal to 3 by 2 kBt, because 3 times half kBt is for translational and 2 times half kBt is for rotational. So we end up with 5 by 2 kBt. Now following this equation, it's just derivation. So let's see how it works. So U upon N, that is the energy, kinetic energy per unit molecule is N, is equal to 5 by 2 kBt. And if you just check this part, number of moles, this is number of moles, and this is number of molecules, and Na is your Avogadro's number. Now if you check this, I can just move this Na on the other side and I get N times Na. So in case if you have followed my just one video before this video, you would not find out anything new about this. So I would highly request you to go and just check for specific heat capacity for monoatomic gases. Okay, so in place of N, I'll write as N times Na. So I'll get U upon N times Na equal to 5 by 2 kBt. This will give me U upon N equal to 5 by 2 Na into kBt. I have just moved this Na on the other side. Now what is this? What is this term? This term is nothing but kinetic energy per unit mole, for a unit mole. Okay. Also I can say that Na into Kb is nothing but a universal constant, that is R. So wherever there is an Na into Kb, I'll write as R. So my equation turns out to be like this: U upon N equal to 5 by 2 RT. Now what I am going to do is I am going to differentiate this with respect to T. So what do I get? Let's see what do we get. So differentiate with respect to temperature. So I get du by n dt. Now n is a constant, so you have thrown it outside, and it is differentiated with respect to t, so I have written as t. Then 5 by 2 is a constant, so 5 by 2 is a constant outside, r is a constant outside, and derivative of t, it's something like this: derivative of t with respect to t is 1, and because it's 1 we do not write it, so that's why we are not writing 1 over here. Okay, so there is a derivative of t with respect to t here, but then this value comes out to be as 1, so 1 we don't write. Now we have also understood about this fact that this term is nothing but your specific heat at a constant volume, which is equal to 5 by 2 R. Now once you are through with this, the rest part is just a walkthrough. Let's say now we use by Mayer's equation. So by Mayer's equation, we can just simply write Cp minus Cv is equal to R. So Cp would be equal to R plus Cv. This Cv goes on the other side, and Cp would be equal to R plus. Now Cp is 5 by 2R, so I am going to substitute Cv as 5 by 2R here. So my equation would become 5 by 2R. Now just solving this, we'll get this is 2 ones are 2, there is a 1 over here, so 2 ones are 2, 2 plus 5 is 7, so I'll get 7 by 2R. So this will be 7 by 2R. So I have found out Cv, and I have found out Cp, and it's just a matter of time when we are landing with ratio of specific heat. So ratio of specific heat, which we denoted by gamma, is equal to Cp by Cv. So gamma would be equal to Cp is 7 by 2R divided by gamma Cv is 5 by 2R. So this is 5 by 2R. So I can say that R gets cut, 2 gets cut, so we land up with gamma to be equal to as 7 by 5. So this is the ratio of specific heat for a diatomic gas. This is for diatomic gas. Also it should be for a rigid rotator. So in case if it is not a rigid rotator, then this value would have been different. So it works both ways. If the ratio of specific heat is 7 by 5, it has to be a diatomic gas, and if it's a diatomic gas and if the molecule is a rigid rotator, then its gamma ka value works as 7 by 5 or 7 by 5. So I hope you have followed this thing. This is the second part which we did for diatomic gas. Initially we did for monoatomic gas. So we'll wind up for today. Thank you so much. Please subscribe the channel in case you haven't so, and keep following the videos. Please follow it in a link, because each and every video is linked to the previous one. In case if you do not follow any video, just go back and listen to the previous videos. Thank you so much. Bye.